Hello and a warm welcome. I'm Joshua, and today, as part of the Digital Fabrication Basics seminar at the Digital Design Unit led by Professor Oliver Tessmann at TU Darmstadt, I'm going to show you how we can plan and construct a three-dimensional installation using flat sheet or paper materials. First, we will build a three-dimensional geometry using the modifier principle Attractor Logic, which you may already know and be familiar with from the Digital Design Basics seminar, and to which we will link the related tutorials. Then we will unfold the geometry and prepare the surfaces with connection parts and markings. And yeah, let's just get started. We start directly in Grasshopper. Grasshopper can be opened by clicking on the green icon under the Standard tab, or by entering the command Grasshopper right here. And the geometry we want to create now consists of several truncated pyramids, each with 4 visible faces. And the pyramids have a square floor plan, so we can create a grid of rectangles. We can start with the component rectangular. Right here, extend the cells, for example, by 3 in X and Y direction. Can go to the perspective mode, or maybe 4. And for each cell, we want to create a pyramid. So we will do 2 things. We will first scale every cell down and move the cells up. We don't need the list structure, so we connect it to a curve component and flatten the list so we get every item in one list. And we want to scale the geometry, so we use the scale component. And now we can see that we scaled the geometry in one direction, but we want to scale every cell by itself. We use the area component and receive the areas of every cell. And we can now connect these centroids to the center of the scaling component and scale the geometry down. Okay, just 1. Now we can scale the cells down, and now we want to move the cells up. We use the move component. We want to scale to move them up with the Z unit. Okay. Now we can disable the preview for these components. We got our cells on the ground and the cells above them. The input are the curves, so we have to merge these 2 curve lists together. But now we can see that the output or the geometry is somehow broken. So when we take a look into the list structure, we can see that the merge component merges these 2 lists into one single list. And these are the 2 lists. And the first item, so index 0 and here index 0, represents a curve pair. So we want to tell the loft component that it has to loft the the first item of the first list with the first item of the second list, and so on. And therefore we have to graft these lists. And when we use a new curve component, graft this list, we can see that each item has its own list. We will also do this with the other list. Graft it. Now we can see that every item has its own list, and when we use these components, now it works, and we can see that the first list is merged with the first list right here, so we got two items. So here we can see the list path or the list index, and it has here the same index or path, and here also. So it merges these two items together in one list, and therefore we can work with this list structure. So it's important to graft these two items or these two components. Now we receive the surfaces. So here we create these surfaces, we can group them and move them right here. But we can see that every pyramid looks the same. And we want to work with the attractor logic. So we can use a point or a curve. And we will start creating a point with construct point, yep. And we can just type in some values. You can, of course, create a point directly in Rhino and import it to Grasshopper by right-clicking on a point component, set one point, and now you can move this point in Grasshopper. Depends on you how you like it. I will just do it right in Grasshopper, right here. Now we got an attractor point in the air. We want to modify the scaling factors and the height. So for example, when a pyramid is closer to the attractor point, the pyramid should be taller, and therefore we have to modify for each pyramid an vector for the move component and translation vector, and we want for the second parameter the scaling factors. So for example, if the pyramid is closer to the point, the openings should be smaller. And now we have to measure for each cell or each pyramid the distance to the attractor point. We can use the centroid and measure the distance with the distance component, or we can also use the vector to point component and connect every centroid with the attractor point, and we receive the vectors and the length of every vector. And with these length factors, we want to modify, or we want to use these factors for the scaling factor and for the translation factor. But we can't just use these values like this, because then the geometry will be broken, and we want to have control over these values. Now we want to change these values without changing the percentage distances between the values. So I constructed an overview. For instance, if these are our length values, they are represented on a line, and we can also display them as percentage values, and the smallest value represents 0% and the largest value represents 100%. And now we can change these numbers without changing the percentage values which they represent in this system. So we can change these numbers, but the distances to each other are still the same. We can change the domain start and end, and the values in between will be recalculated. So we can do this in Grasshopper with the component remap numbers. It asks for the values to remap, which are the length values, and then a source domain and a target domain. And the source domain is the smallest and largest value of this list, and we can receive these values with the bounds component. So now you can see it's written like that. We have the smallest and the largest value in one list. We can use this as the source domain, and now we can construct our own domain with construct domain, and this is our target domain. And we can, for example, choose these values, and now we can take a look at the results. And here we can see, maybe I will start with 1 or with 100. So now we can see that the smallest value right here has index 8 is now 0 because we set the domain start to 0, and the largest value here on top has now the value 100 because we set the domain end to 100. So therefore we can remap or recalculate the values in between. And don't get confused, the list is sorted downwards like this because the attractor point is located here. When we move the attractor point to another position, for example to the center, then we can see that the smallest value is in the middle of the list. Just that you don't get confused why it's sorted like that. It's just because of the length values right here in this list. So with this workflow we can rearrange or recompute the values and use them as our scaling factors. Okay, this we have to use smaller values right here and start. Okay, these values are too large, so I will modify the slider components by, for example, okay, and now we can modify the scaling of the upper cells. This is the principle of the attractor point, Attractor Logic. And we can do exactly the same for the translation vector and control these parameters. So now the pyramid, which is closer to the attractor point, is taller than the others. And you can of course use more complex attractor logic with curves instead of one point, and we will link the related tutorials to this video. This is the basic attractor logic principle. Now we can organize our canvas a little bit. So here is the scaling part. So we can use under the Parents tab the scribble component. And vectors. At the moment, we just move the downscaled cells upwards by a Z value in Z direction. And the next goal is to orient the pyramids towards, just a little bit towards the attractor point. At the moment we just use a Z vector and changing the factors for this component, but we want to use the vectors from each centroid to the attractor point. Therefore, we will use these vectors, and we have to change the vector length, and we can do this with the vector amplitude component. Oops. And use our new remapped numbers as the amplitudes. These are our new lengths. And then we can use the new vectors instead of these. And we can see that this effect is a little bit too extreme, so we can use both vectors. We can use the new vectors and the Z vectors and add them up together. And we can change the amount by multiplying this vector . So if we multiply this vector by 1, it will stay the same. So we can decrease this effect with a Z value. So we created our first geometry, and don't forget to save your document.